Hello viewers, it's good to come your way again in another session in mathematics, and in this session I'll be discussing integration, the second part of calculus. In the previous session I discussed what differentiation is all about and all those things about differentiation, even up till the application of differentiation, where I discussed what we call the extrema of functions, talking about minimum and maximum points. In this particular session I'll be discussing integration, and of course it is important to note that integration is the reverse process of differentiation. That is why sometimes integration is called anti-differentiation. When you differentiate a function, what you obtain is called the differential coefficient of a function, and when you integrate the differential coefficient of that function, you obtain the original function back. When you differentiate sine x, you have cos x, meaning when you integrate cos x, you are expected to have sine x back. So in integration now, we'll just be doing the reverse process of all those functions we had differentiated earlier in the other session. Alright, so that's what integration is all about, and as you can see on your screen, what I have to establish as far as integration is concerned is the general integration principle, okay, the standard integrals we have, what is known as integration of function of a function, like chain rule now, okay, definite integrals, and of course we'll look at one application of integration, talking about area under the curve. We have other applications like volume of solid revolution, but of course in this tutorial we're looking at the scope of what is expected of you at the end of the day, so I'm just sticking to that scope. Alright, so if you see on the screen, the first is to establish what is known as the general integration principle, the approach that is always to be used whenever we are integrating. Alright, so on your slide, on your screen now, you can see if I have a function y equals to f of x, and it can be written as a function of x, that's x raised to power n. In differentiation, we bring the power down and we subtract 1 from it. But in integration, if I'm to find integral of f of x dx, integral sign is there, okay? Integral of f of x dx, this is going to give me integral of x raised to power n dx. These are things I want you to observe. Anytime we are integrating, now there are three things that are always present. One is the integral sign. So if you write an examination and you are asked to integrate and you see this integral sign, or maybe you are given a question to evaluate and you see that sign there, that means you are integrating. Now the second guy is what is inside here, that is the function you are integrating. This guy is called the integrand. The function you are trying to integrate is called the integrand, and of course this guy is always the dx, to tell you that you are integrating with respect to x. You are integrating with respect to x. You know, in advanced calculus, when you talk about line and multiple integrals, you can have more than dx, you can have dx, dy, dz when you are talking about multiple integrals. Alright, but at this level now, we just talk about dx, meaning anytime we are to differentiate and integrate as far as this course is concerned, all of that, both of them are always done with respect to x. dy dx, you differentiate with respect to x, and also integral of f of x dx, you integrate with respect to x. So these are the components of a given integration question. Alright, so this is how we integrate. So integral of f of x dx is equals to integral of x raised to power n dx, since our f of x was given as x raised to power n. Okay, so I'm just going to write the general formula expression for integrating. So whenever we integrate, we just add 1 to the power. So we have x raised to power n plus 1, and divide by that again, n plus 1 plus k, provided that n is not equals to minus 1. I will explain. Alright, so this is how we are going to integrate as far as integration is concerned. You always add 1 to the power of x and divide by that new power you have. That is after adding the 1. And you always introduce the constant. I'll tell you why the constant is necessary. Alright, so on your screen you can see that if I'm to evaluate integral of x dx, x squared dx, I want to integrate x squared dx. Okay, so what I'm integrating is x squared. The general integration principle says we add 1 to that power and we divide by that. So I'm going to have x raised to power 2 plus 1 divided by 2 plus 1 plus k. So this is going to give me x raised to the power 2 plus 1 is 3 divided by 2 plus 1, which is also 3 plus k. Now that's how we integrate. So integral of x squared dx is x raised to the power 3 divided by 3 plus k. Now integral of x raised to the power 5 dx, another example, is actually x raised to the power 5 plus 1 divided by 5 plus 1 plus k. You can use k, you can use c, you can use any number you want to use different from x, okay, as your constants. Alright, so you always add 1 to the power of x divided by that. So this is now equals to x raised to the power 5 plus 1 is x raised to the power 6 divided by 6 plus k. That gives us the integral of x raised to the power 5 dx. Now if I were to evaluate integral of maybe 1 over x cubed dx, okay, 1 over x cubed dx, this can be written as integral of x raised to the power minus 3 dx. 1 over x cubed means x raised to the power minus 3. You must always write it that way first. Don't forget one of your laws of indices, that a raised to the power minus m means 1 over a raised to the power m. So if I have a raised to the power 1 over a raised to the power m and I want to write it as a single term, okay, that's just one single guy, no numerator, no denominator, then I can translate 1 over a raised to the power m as a raised to the power minus m. Okay, so that inverse is the negative of the power. So yeah, I'm having inverse of x cubed, that's 1 over x cubed, which means x raised to the power minus 3 according to the rule in indices. Okay, that's now when you now integrate. So you have x raised to the power minus 3 plus 1 divided by minus 3 plus 1 plus c as our constants. So this will give us x raised to the power minus 3 plus 1 is minus 2 divided by minus 2 plus c. Okay, since x is raised to a negative power here, I can choose to bring it down again. So if I bring it down, 1 is left on top. So I'm going to have minus 1 over 2x squared plus c at the end of the day. That is how we integrate. Just to be sure you understand what I'm saying, I'll still take more examples. Now if I were to integrate 1 over x dx, when I wrote the general formula, I told you that for you to integrate x raised to the power n, you have x raised to the power n plus 1 divided by n plus 1, provided n is not equals to minus 1. See what is going to happen here. If I were to integrate 1 over x dx, I'm going to have integral of x raised to the power minus 1 dx, because 1 over x means x raised to the power minus 1 from indices. Okay, so this now equals to x raised to the power minus 1 plus 1 divided by minus 1 plus 1. Sorry, let me erase this so I can write it again for you to see. Okay, so our n is minus 1 now, so we add 1 to that power of n divided by that again. So we have divided by minus 1 plus 1, then plus c. Now you now observe that you are going to have x to the power minus 1 plus 1 here is 0 divided by 0. So this guy you are having here now, divided by 0, does not exist in maths. Anything divided by 0 in mathematics is undefined. You cannot define it mathematically. There is no solution or approach for it at this level for you to be able to evaluate that. We always try as much as we can to make sure we avoid 0 being the denominator of anything in mathematics. So if I want to integrate 1 over x using the general approach, I'm going to have 0 as the denominator. So that rule for integration x raised to the power n dx, which I told you is x raised to the power n plus 1 divided by n plus 1 plus k, is only applicable whenever n is not equal to minus 1. You know, once n is equal to minus 1, that guy will never work. So that rule is only applicable wherever n is not equal to minus 1. And n will be equal to minus 1 when you have 1 over x. So that integral of 1 over x cannot be evaluated using this approach. We are now going to recall something. Now, one of those things I did not mention in differentiation, because actually it was beyond the scope of this tutorial, was that we can have the derivative of logarithmic functions. That's logarithm now. Logarithms. Okay? Now, if you differentiate a log function, you have the first log function as log x base a, something like log x base 10, log x base 20, and the rest. When the base is different from anything, it's just a constant a. The derivative of log x base a is 1 over x ln a. Okay? Well, it's rather unfortunate I can't show you how I got that, but I just want you to take note of it. Now, number 2, because of time, I would have shown you. Number 2, if you have another log function as log x base e, where e is the natural base, log x base e. Log x base e is translated as ln x in mathematics. Log x base e, where e is the natural number, is translated as ln x in math. And in mathematics, when you differentiate ln x in math, you are going to have 1 over x as the derivative of ln x. Because of time constraint, I cannot show you that. Okay, so when you differentiate ln x in math, you have 1 over x. So meaning, if I'm trying to integrate 1 over x dx again, which will not work using this general approach of adding 1 to the power divided by that, I'm going to recall that the derivative of ln x gave us 1 over x, meaning that the integral of 1 over x will give us ln x back. So in mathematics, as a standard integral now is that anytime I integrate 1 over x, I'm going to have ln x plus k. That is just what is used at any point in time. Anytime you integrate 1 over x, you cannot use the general integration principle of adding 1 to the power. So you always need to recall that the derivative of ln x gave us 1 over x, meaning that the integral of 1 over x is just for you to write ln x plus k back. So that's that. And finally, still talking about how to integrate. If I integrate a constant, integral of 5 dx will give me 5x plus k. Anytime you integrate a constant, you add x to that constant, because if you differentiate 5x, you are going to have 5. So integrating 5 will give you 5x back. Okay, so if I integrate 7 dx in math, I'm going to have 7x plus c. If I integrate 10 dx in math, I'm going to have 10x plus c. That's how we differentiate a constant. Integrate a constant rather. If you integrate a variable x, so integral of x dx means add 1 to the power of x there, which is 1, so you have 2. So that will give us x squared over 2 plus c. This is how we integrate. Now, why we add the constant anytime we integrate is because we are always integrating what is called the derivative of a function. When you differentiate 5x, you have 5. Meaning when you integrate 5, you have 5x back. Anything I'm given to integrate is considered as a derivative of something. And you notice that anytime you differentiate, a constant is always lost. For instance, I have x squared plus 5. I have x squared minus 10. I have x squared plus 8. In each of these functions, if I differentiate, my dy dx is going to be 2x in all of them. Differentiate all those constants, they differentiate plus 5, I'll have 0. Differentiate minus 10, I'll have 0. Differentiate 8, I'll have 0. Okay, so if I'm now asked to integrate 2x dx, so I have integral of 2x dx, means add 1 to the power, divide by that. So that will give me 2x raised to the power 1 plus 1 is 2 divided by 2. So here you notice that if 2 and 2 cancels, you are going to have x squared back as an integral of 2x dx. You have x squared. Now, the x squared does not correctly represent the original function that was there before, which in this case, the function might have been x squared plus 5, might have been x squared minus 10, might have been x squared plus 8. But after the integral now, you're having just x squared alone without the constant. That is why anytime we integrate in math, we always add plus k or plus c, depending on any of them you want to use, to represent the constant term that was lost during the process of differentiation. Because anytime we integrate, we expect that we're integrating a derivative of some function, we might not have known. Okay, so there was a constant that maybe was lost during the process of that differentiation. So anytime we integrate, we always add a constant. So integral of 2x dx will give me x squared plus k. So this k here, for this first one, represent the plus 5 that was there. For this second one, will represent the minus 10 that was there. And for this third one, will represent the plus 8 that was there. Alright, since we did not know it actually, so we can't actually write a specific number. So we'll just write the plus k to represent a constant that must have been present in the original function. That is what integration is all about, and in this particular session, I've succeeded in establishing how to integrate. Add 1 to the original power, divide by that plus k. That is how we're going to be integrating. Alright, in the subsequent videos, I'll take you fully into the lecture of establishing what I call standard integrals, which we'll be using frequently. We'll look at integration of function of a function, of course definite integrals too, and of course application of integration, talking about area under the curve. Don't go anywhere. Let's meet in the next session as we proceed as far as integration is all about.